So welcome all to week 4 tutorial for the course Essential Mathematics for Machine Learning. I'm Pintu Kumar. I'm a PhD scholar at IIT Bombay. So the topics that I plan to cover today is PCA and as well as I'll cover LDA, so Principal Component Analysis and Linear Discriminant Analysis. I won't go into the proof of these methods, but I'll try to convey how you can find principal component or how you can convert vectors to low dimensional space. That is the use of these two kind of conversions that I'll try to convey. Okay, so initially for the 10-15 minutes, we might spend some time covering some basics of probability and statistics, defining what is mean, standard deviation, covariance, and those kind of things, as they are useful in doing principal component analysis or LDA. Okay. So anytime during today's lecture, if you have any doubt, you can either unmute yourself and ask the question, or you can type it in the chat box. I'll try to resolve your issue. Okay. Okay. So first of all, let's try to understand why do we need something like PCA or LDA. Okay. These methods, what they do is they convert high dimensional feature vectors to lower dimensional feature vectors. Okay. Now, first thing that I would like to sort of just convey is that, for example, if you do any machine learning task, generally you will have data of this form. Okay, so you will have some data points, let's say x1, x2, x3, xn. Okay, and you have some corresponding feature 1, feature 2, feature 3, and so on. Okay. So before going to PCA or LDA, I would just like to mention. So if I talk about dimension of like feature vector, or I talk about dimension of a data set, so you might have heard terms like high dimensional data set or high dimensional learning or those kind of things. So that dimension is related to the number of features that you have. Okay, so this is number of data points. And this is number of features that you have. Okay. So if you have more and more data points, that's never an issue, right? If you have more data points, it will help you generalize better. And generally, in machine learning tasks, you demand for more and more data. So it's an unsaid rule. So if you have more data, better it is. Okay. Okay. But the same is not true with features, right? If you have too less feature, then it's a problem. But sometimes if you have too many features, then also it becomes a problem. Okay. For example, if you have lesser number of data points, okay, so lesser number of data points, then the features, the number of features, this then becomes the problem of high dimensional statistics or high dimensional learning, and you will have to do something extra just rather than just applying your methods freely. Okay. Also, now I'll try to motivate why, in what kind of situations do we need PCA or LDA. Okay. So sometimes your features might be correlated. Okay. For example, let's say you measure height of a person, you measure weight of a person, and you have a feature that is, let's say, height plus weight. And then you might have some other features. So this third feature is nothing but a sum of earlier two features. Okay. So these three features are correlated. So or I would rather say this height and height plus weight are correlated to each other. So if you have both these features in your data set, then these features will influence your predictions more as compared to other features that you have. So if you repeat a feature, that would lead to more influence on your prediction. Okay. So if you have a data set where you have correlated features, or you can say multi-correlated features, then you want to remove that correlated features. So you, let's say you want to ignore these kind of features. Okay. Here you're, so in that kind of situation, you use PCA or LDA. Okay. Now one more thing. Here your correlation was straight, I would say direct, because you were just adding height and weight. Okay. But in some situation, your correlation might not be that. So I'll define what correlation is, but correlation would mean that if you increase one of these things, the other feature should increase too. Or if you decrease one of them, the other features should decrease too. Then those two features are said to be correlated. Okay. So yeah. For example, your height and weight are also correlated. So if your height increases, generally the weight would increase. Okay. But the correlation value over here won't be 1. It would be slightly lesser than 1, right? So these kind of correlation, so if you had correlation of earlier type where you had height plus weight, you could have just ignored this feature, right? But if you have a correlation of these kind, you can't ignore one of them. But you want to combine both of them in a fashion that you can obtain a single feature out of it. Okay. So in that kind of situation, your PCA and LDA kind of helps you. Okay. So role of this PCA or LDA is to reduce your high dimensional feature vector to a lower dimensional feature vector. Okay. Another advantage of using LDA or PCA can be, so many a times you apply some algorithm on your data set and you want to visualize that data, right? Okay. But you can't visualize anything in dimension more than 3, or the even like on a plain piece of paper, you can visualize it in dimension 2, right? So in those kind of situations, you can convert whatever output you have obtained or the data that you have, let's say two-dimensional feature, and then you can sort of visualize them. So if you are able to visualize them, you might have a better idea what kind of architecture do you want to use, what kind of model do you want to use. So in these kind of tasks, your this dimension reduction techniques are useful. Okay. Any doubt till this one? I hope no. Okay. Okay. So yeah, this is what I have written over here. So your PCA maps your higher dimension data to a lower dimension data. So higher dimension data means more number of feature, and lower dimension data means lesser number of feature. Okay. And also you want to sort of reduce this dimension in such a way that you don't lose a lot of information. Okay. So you also try to preserve a lot of information that you have in the data. Okay. Okay. So I'll just go through some elementary things. Okay. We haven't covered something called as random variables as of yet. That I think would be done by another professor. So I think it would be in week 6 or 7. So I'm not defining these terms right now for a random variable. What I'm defining it for is, let's say you have collected some data, for example, x1, y1, x2, y2. So this kind of thing is known as sample. So whatever I'm defining is for this kind of sample. So I'm defining sample means sample variance and those kind of things. Okay. Okay. So what is mean? Mean you all have, I think, have come across at some point in your life. It is another name for average. Okay. So average is just sum of all the entries divided by number of entries. Your n over here is number of entries. I'll try to go quickly over it. If some of you have doubt in this, please stop me there. Okay, because I'm going to quickly go over these elementary things. Okay. So here is a simple example. So So there is some soccer tournament that is held each year. This season, in 10 games, the lead scorer for the home team scored these many goals. Okay. So it is asking what is the mean score of this player. Okay. So mean score is sum of all scores 7 plus 5 plus 0 plus 7 plus 8 plus 5 plus 5 plus 4 plus 1 plus 5 divided by number of games that he has played. So it is mentioned 10, otherwise you could have also counted it. Okay. So this I think is 12, then 27, 37, I think 47 divided by 10, that is 4.7. You just check the calculation. I'm not confirming it. You can check the calculation. But this is how your mean is calculated. Okay. Okay. So why do we define first of all these kind of things, mean, variance, or these kind of things? Okay. So one thing is, like if you have a sample, let's say you have a data point. Okay. So rather than using all these points to define this set, what you want to do is you want to represent this data using some quantities or lesser number of values. Okay. For example, you want to represent this data by mean of that data. Mean gives you a lot of idea, right? So for example, if you have two players, rather than just keeping a count of their scores in all the games, what you can do is you can just keep a track of their mean score, and that mean score will tell you a lot about how that player has performed. Okay, so many of you watch cricket, right? So when you see stats of some player, you don't see their score in every individual match. They just show you the average, right? That average is slightly different from here. They divide it by the number of times the player has got out, but that's just a slight change. But yeah, they just show you the average rather than showing their scores in every match, and you get an idea how good or bad that player is based on that average that you see. Okay. So similarly, we see the average over here. Okay. Now, before introducing next term variance, let's look at two data. Let's say these are scores by two players. Okay. So in three cricket matches, first player scores, let's say 95, right? Then he scores 0-0, or maybe let him score 99. Okay. And the another player scores 33, maybe 32 and 34 in three matches. Okay. So if you calculate mean of these two, both their means are 33. Okay. But these data are not same, right? In one of the matches, the player has scored a very high score, but has failed in other two. So you can see that the player is not consistent. Okay. This player, on the other hand, has scored lesser number of runs, but is sort of consistent across matches. Okay. So if you just represent these value by just his average, that does not give an idea about what kind of player he is. Okay. So we want to define something more that is known as variance. Okay. Variance gives you an idea how far are individual data points from the mean of the data. Why is it not handling space? I will try also. I think they rolled out some update for this OneNote, and yeah, it's not that great. Okay. So what I was saying is that more than mean, we need something more that can capture how like how close are these individual data points, or how far are they from the average. Okay. So to do so, what we do is we like sort of write the distance from the mean that for every data point. Okay. For example, if the average is 33, the distance over here is 66. This is minus 33. This is also minus 33. And for the second player, it is 0, minus 1 and 1. So you can see that the second player's scores are much closer to the mean as compared to the first player. Okay. Now, like in mathematics or any other area, when you try to find out error, okay, when you try to find out error, you don't simply add the errors. Generally, what you do is you either take mod of that error or you take square of that error and then add, so that your signs are taken care of. Okay. So what we did was, so we did xi minus mu. We want to look at its sum, the total error that it is committing. But to take care of the sign, we just want to square it. Okay. And also we want to divide it by number of data points. Okay. Now there is a slight comment that I want to make. If you divide by the number of data points in statistics, if you will go through a probability or statistics course, this estimator of variance is called as an unbiased estimator. Sorry, it's called a biased estimator. Okay, it's a biased estimator. And there is another variant of it proposed. So you divide by one lesser number. So if you have n data points, it was divided by n minus 1. And this is an unbiased estimator. Okay. So when you calculate sample variance, you divide it by n minus 1 rather than n. So this term is defined as variance of your data. Okay. And it's represented by sigma square. Your mean was represented by mu. Okay. We use mu to represent the mean.
Sir, is that n minus 1 represents the degrees of freedom or anything?
No, it's just the number of data points. So when you take expected value, the n minus 1 sort of converges to your actual population variance, whereas this earlier one don't. So you just divide it by n minus 1. So okay. So this is represented by sigma square. Okay. And because we took a square, we now take a square root. So, and this quantity is called standard deviation. Okay. This quantity is called the standard deviation. Okay. So here is a small example that we can do. Okay. So we have to calculate the variance of this data set. Okay. So first of all, we will calculate the mean. Mean is 2 plus 7 plus 3 plus 12 plus 9. So there are 1, 2, 3, 4, 5 data points. So we'll divide it by 5. So 24 and 9 is 33 by 5. So this is the mean. And then you can calculate, so 33 by 5 is 6.6. You can subtract 6.6 from every entry. So this is minus 4.6 square plus 0.4 square plus 3.6 square. This is minus plus 5.4 square plus 2.4 square. And then you can divide it by 4 because there are 5 data points and you'll get your variance. Okay. This is how variance is calculated. Okay. Now we come to something that we want to do, because this covariance will be used in PCA and those kind of things. Earlier, whatever we have discussed till now was just to motivate this definition of covariance. Okay. Now let's say you have two features, x and y. Okay. And you want to see whether they are related to each other or not. Okay. So what will happen? You will have first data point, let's say x1, y1, x2, y2, x3, y3, and so on. Right. Now, let's say if this value and this value is related, your x and y are related, then what should be your expectation from x1 and y1? Okay, so what I'm claiming is, let's say my x1 is greater than mean of x1. So I take the mean of this only x features, I call it mu x. If my x1 value is greater than mean and these two values are sort of correlated, then what should I expect? I should expect that y1 should also be greater than its mean, right? Then only they can be, in a sense, related that if I'm increasing my x1, then my y1 should increase too, right? So what I'm saying is, if my x1 is greater than mu x, then I should expect that my y should also be greater than mu y. Okay. So what I do is, I take the difference between xi and mu x. So if this is positive and this is also positive, then their product will also be positive. And similarly, I do for all the data points. So if my covariance I obtain and I sum it up, okay, and then just a scaling factor 1 by n. Here also, you will divide by n minus 1 when you have unbiased thing. You can use both this formula, but I'll be using n minus 1 for calculations. Okay. Yeah. So if this value is positive, then I can say that the two features are related to each other, or I can say positively related to each other, right? And the other way around, if my x1 was greater than mu x and my y1 was less than equal to mu y, then this first term was positive and the second term was negative. So the product is negative and the sum should, I should get negative. So they are related, but in an opposite manner. So if my x is increasing, my y is decreasing. Okay. So they are called negatively related. Okay. So this is how my covariance is defined. This is x minus mu x multiplied by y minus mu y, and you sum it over all the data points. Okay, and divide by scaling factor 1 by n, 1 minus 1 upon n minus 2. Okay. So this covariance of x comma y gives you covariance between two features x and y. Okay. Now we talk something about covariance matrix. Okay. So there would be very rare chance where your data set will have only two features. In general, you will have more features. Okay. So let's say you have features f1, f2, so on till fn, right? And corresponding data point x1, x2, x3, so on. Then you can define something known as covariance matrix. Okay. Where your first entry is covariance of f1 with f1 itself. So you are checking covariance of f1 with f1. I'll tell you why it is. For the second entry, you have covariance of f1 with f2. So we discuss how we can find covariance between two features. Now you want to find covariance between feature 1 and feature 2. Then you have covariance between feature 1 and feature 3, and so on. Similarly, over here you have covariance between f2 comma f1, then covariance between f1 comma f1, right, and so on. Similarly, you can fill in this complete matrix to obtain a matrix that is called as covariance matrix. Okay. I should remove this because I used X. The notation can be confusing for someone who is reading it later. So let's stick to F. Okay. Also, you can see that covariance of a feature with itself. So if you look at the covariance formula, it's x minus mu x multiplied by x minus mu x. So it becomes x minus mu x square, and this is nothing but your variance. Okay. So this is variance of x, right? So this entry can be replaced by variance of f1, right? Variance, this would be f2. I'm sorry for the typo. This is sigma square f. Okay. Okay. So this is how covariance is defined. Okay. Now I'll just take a small detour. Okay. And tell you something. Okay. So then let's say you have a data matrix. So data matrix is nothing. This is your feature 1. This is your feature 2. This is your x1, x2, x3, x4. These are your 4 data points. Okay. So I want to find the covariance matrix for this data matrix. Okay. So first entry would be sigma square of f1. So it would be a 2 cross 2 matrix because it has 2 features. Then this will be covariance of f1 with f2, covariance of f2 with f1, and then sigma square f. Okay. Now what I am saying is, let's say your data matrix, for every feature the mean is 0. So your mu of f1, mu of f2, these things are 0. Okay. Now what was the formula of covariance? Covariance was 1 upon n minus 1, summation I is equal to 1 to n, where your n is number of features. Sorry, yeah, this is number of data points, and this is xi minus mu of okay, so I should write covariance of f1 and f2, right? So this is f1 multiplied by x minus, sorry. So this is x1, so I can call this entry as x11 and I can
Should
call
be
this
f1 minus, it should be f1 minus mu f1, right?
yeah, f1 is the name of feature, but data point I can represent by x11 and x12, right? So I can call it xi1 and I can call it xi2 minus mu of f2. This is just the notation that I'm using, right? So it is same as, so we had 2 features x and y here. Now we have f1 and f2. So that's why something like this. Yeah, something we can use a notation, something that you suggested, but I named it x, so I'm using xi1 and xi2. Okay. So if my mean is now 0, okay, these 2 entries, if they are 0, if these are 0, then this formula reduced to 1 upon n minus 1, summation I is equal to 1 to n, xi1 multiplied by xi2. And this is nothing, if you carefully see, this is 1 upon n minus 1. So this feature vector f1 transpose f2. Yeah, so this is, I think, correct. So if you take, what you want to do is you want to multiply the first entry with the first entry over here, then add second entry to the second entry, third entry to the third entry, and so on. So this is just the dot product that you can obtain. Okay, if my mean is 0. Okay, so now if I want to obtain my covariance matrix, right? What is my covariance matrix? This is nothing but okay, covariance of f1 with f1, covariance of f1 with f2, covariance of f2 with f1, and covariance of f2 with f2, right? And we know if my mean is 0, that formula would be replaced by this. Okay, so let's try to, I think in the lecture the formula was directly given. I'm trying to sort of explain why that formula is like what it is. Okay, so we can take, so all these terms will have 1 upon n minus 1. So we can take this 1 upon n minus 1 as common, and then we will be left with f1 transpose F2. This is, oh, sorry, this is F1 transpose F1 because we are taking the covariance with itself. This is F1 transpose F2. This is F2 transpose F1, and this is F2 transpose F1. Okay. Now, if my C matrix has column F1 and F2, right? And I want to obtain something like this from here. So if I take C transpose, which is this, so if I take C transpose multiplied by C, so C transpose would be F1. Okay, so this is sort of F1 transpose because now I'm writing it as rho and right. So if you look at this product, the first entry would be F1 as a row multiplied by F1 as a column, that is F1 transpose F1. Second entry would be F1 transpose F2. Third entry would be F2 transpose, and so on. You can obtain the same matrix. Okay. So what I'm saying is, if you have a data set, and for every feature, you make its mean 0, right? Then you can straight away obtain your covariance matrix as 1 upon n minus 1 C transpose C. Okay. The only condition is that your mean should be 0. Then only you can do this thing. Okay. So I think we didn't had a question. Now we have a question on this. I had a question. Where did I write it? I had. Just give me a second. That's how we went to this calculation. Yeah, this was the question. Okay. So I'll copy paste it slightly fresh. Okay. So I'll erase this unnecessary things that I have done here. Okay. Okay. So we are given with the data matrix C, and we have been asked to calculate the covariance matrix, right? Now we saw if your mean is 0 for every feature. So if you look at this 3 and 3 cancels, minus 1 and 1 cancels, so the sum is 0, so the mean is 0. Similarly, over here you can see the mean is 0. So both mu x as well as mu y here is 0, right? So we can apply our formula over here. So the covariance over here would be given as, so what is the number of data points that you have? You have 1, 2, 3, 4 data points. So your n becomes 4. So you're going to have 1 upon n minus 1 is 3. That being multiplied by C transpose, right? C. Okay. So what is the answer? I'll not won't calculate it using my hand. I'll use MATLAB probably. I'll share my screen and show you how we can calculate from MATLAB. Okay. For matrix multiplication, MATLAB is pretty handy. It gives you very easy way to calculate. So my C matrix was given by minus 1, 2. I'm writing the first row. Then the second row is minus 3, minus 2, minus 3, minus 2. Then 3, comma 1. This is 3, 1. And the last row is 1, minus 1. Right? So this is my C matrix. This is what we had. Now what I want to do is, I want to do C transpose multiplied by C. this is what we will obtain. So this is 1 by 3 20 6 6 10. Right. So this is the covariance matrix that we have obtained. Okay, this is the covariance matrix. Okay. Any doubt till this point? I would be happy to answer.
So far it is clear. I have a doubt that when we are doing assignment problems, you can use MATLAB, right? But in the final examination, there won't be any software installed in the system. So some complicated problems in the matrix, how can we solve
Uh,
without using MATLAB and Python?
yeah, that won't be possible. So I think the professor who will decide the question will keep this in mind, and I think you will get easier matrix over there. So if you have to do this kind of computation, the multiplication won't be that easy. So there are many questions in the assignment that don't explicitly wants you to multiply matrices or those kind of things, but they just want to test your knowledge. Right? For example, I think we have some questions over here. No, we don't have. But you have questions like you are given with principal components and you just want to find the projection of data points. I think those kind of questions would be more asked. But again, that depends on the professor who is setting up the questions.
Sir, can you discuss that thing, the projection of the matrix? So,
We will go.
in the lecture video, it is not available. I think so. Sir. The projection
I think
concept of problems.
it is there. I'll discuss it when I'm discussing principal component. Okay,
Okay,
that's
sir.
what I'm going to discuss next. Okay. Other anyone else has any other doubt?
So basically, when we are finding the covariance, we can use 1 by n when the covariance is non-zero, and when it is zero, no, mean is non-zero, and when mean is zero, we can use 1 by n minus 1.
No, no. So in
Huh.
I think you joined a bit late, but
Yeah, yeah, a bit late, yes, yes, yeah.
okay. So in statistics, there are two things. One is called sample mean or variance. So when you sample from some population, okay. So we call that if you calculate this mean, we call it sample mean or sample variance. Okay. Or when you have the complete random variable or you have the complete population, we call it population mean or population variance. Okay. So because this sample that you have sampled from the original population is an estimate of your complete data. So you don't have the complete data, but you have an estimate. So the variance or the mean that you have, that is also an estimate to the original mean or the variance that you have for your complete data, right? I think I'm making sense. So the mean or the variance that you calculate out of your samples, that is an estimate to the original mean or the variance that you could have. Okay. For example, I'll give you an example. Let's say you have India, right? You consider the complete population of India as the population, and you want to estimate or you collect data of, let's say, 10 lakh people, measure their height, okay, and you report the average height. Okay. Now you have not considered the height of all the peoples, but you have just considered height of 10,000 people probably, or 10 lakh peoples. Okay. So this average is an estimate to the average of the mean, sorry, average of the population, complete India. Okay. So in that sense, this mean or the variance that we are calculating based on the data that we have, those are just estimate to the original mean and the variance. Okay. Now the question that you asked after saying this. So for mean, there is no confusion. So for mean, you have summation I is equal to 1 to n xi, right? This is the mean. So this is how you estimate mean. Okay. Now to estimate variance, there are two methods. Okay. One is you divide it by n, summation I is equal to 1 to n xi minus mu square. Okay. And there is another estimate. Okay. That is 1 upon n minus 1, summation I is equal to 1 to n xi minus mu square. Okay, see, these both are estimate to your variance. Okay, they are not true variance, they are estimate to your variance, as I mentioned. Okay, so both these formulas are correct, none of them are wrong, both these formulas are correct. Okay, but in statistics, if you read some book, there is something called as biased and unbiased estimator. Okay, so what it eventually, I'll just give you an idea. So if you take expectation of these value, okay, this value, this expected value will go to the population variance. Okay, but the above one do not go to population variance. That's why the first estimate is called biased estimator, and the second one is called unbiased estimator, and hence this one is more used. Okay, so whenever you have problems that you see when you have data and you solve in assignment, you stick to dividing by n-1. Okay, so you use this formula only. I hope I was
But
clear.
basically in the lecture video, only 1 by n C transpose, like 1 by n was mentioned. And
I think later he changed the notation to n-1 also, but because this is
oh,
when your n is sufficiently high, this don't make a lot of difference. So people switch between both of them, but second one is more preferred.
okay. Even for assignment, no, I've used n only. But okay, anyway, that is confusing. No, when we are given with just a 4 by 2 matrix, if
Yeah,
one is using n, one is using n, or the other one is using n-1, we'll be getting different answers. No.
different answers. If both are present
Yeah.
in option, then I think you can take one. I can discuss it with the course TA. But I think
Okay. Okay.
only one of them, one of the option would be available. I think if both are available, you stick with n-1.
Okay. I got the answer with using n. That's why I was confused with n-1.
Okay.
That's why. Okay. Okay.
So
Okay.
if you,
Thank you.
okay, somebody asks in the problem how we identify a given is a population or sample. In machine learning or this kind of thing, you always have sample only because you sample from some data set. So you sample from some distribution. You don't know the complete distribution. Okay. So you have some data set and you want to predict on some other data set. That means you don't have the complete data set. You just have a portion of the data set on which you want to train your model or those kind of things. So here you have only samples. Okay, so moving ahead. So initially I told that the goal of principal component analysis or LDA is to find a lower dimensional sort of representation, right? So you want to convert your high dimensional feature vector to low dimensional feature vector. Right. Now question is, how is it done? So now, like I'll tell you whatever I'm going to tell you, that is true for both PCA as well as LDA, but there is a slight difference that I'm going to cover a bit later. Okay. Now what we do is, let's say, I think I have a figure, I can use that here. Okay. I'm just using this figure, we'll solve this question later. Okay. So let's say you have a data point of this type where you have plus point, red points and some blue points. Okay. So this is a two-dimensional data clearly, right? There is x1 feature, there is x2 feature, and you have corresponding points, right? Now what you want to do is you want to convert this data to a one-dimensional data, right? So how should we go about it? Okay. So the approach that people take is they find a line. Okay, they find a line. How we find a line, we will talk about it. But the goal is we will find a line and we will project all our points to that line. Okay. So this is the line. Now this data point gets converted to this point, this point, this point. This will also get converted to this point. This will also get converted to this point, right? And these blue squares will also be mapped here, and this will be mapped here. This will be mapped here. This will be mapped here. Okay. So the way we convert high dimensional feature to a low dimensional feature is, for example, in 2-dimension, you will look for a line, right? And you will project it onto that line. Okay. Now, if you have higher dimension, let's say you want to go from 3-dimension to 2-dimension. Okay. Then you will look for 2 lines. Okay. Or in a sense, you will look for a plane, but you will look for
Plane,
2.
right?
Yeah. Can you please repeat?
So we need to find a plane.
I think your voice initially break. I could just hear the word plane. Can you please repeat?
So in three-dimensional, it will be a plane, right? We cannot have it as a line.
Yeah, that's what I said. So if you want to project from 3-dimensional to 2-dimensional, you can have a span of 2 lines, which is eventually a plane, right? So, but what you want to find over there also is that you want to find 2 lines using whose span you can create the plane on which you want to project. Okay. So if you want to project from some Rn to Rm, your goal is to find m vectors on whose linear span you want to project your data points. Okay. This is how you reduce the dimension of your data set. Okay. So I'll do one thing, right? So let's say, as I said, if you want to go from, yeah, somebody wants to say something.
Is this related to curve fitting in statistics? Why? Because then there also we are having a set of data points and we are trying to find the linear regression or those kind of things, right? Is that the same?
It is slightly different. Okay, so when you have linear regression or curve fitting kind of a thing, your goal is that you want to minimize your prediction error, right? So you have some y, or you want to minimize your prediction error, right? But here your goal is that you just want to capture some information in the data. Okay. So we will see that PCA wants to look for a direction that has maximum variance in the data, whereas LDA looks for a direction uh, which preserves linear separability. So it is slightly different, but yeah, you can, yeah, it is slightly different. The goals are slightly different. Okay. Okay.
Context. No need to deviate the things that the cut in the.
I didn't understood you. Can you please type? Your voice sometimes breaks when you under.
I got little bit fluctuation in my network. So you go with the context that we are having principal component analysis and NDA. So I think I am deviating from the topic, right?
That's fine.
So
Like these are tutorials, these are not meant to be a focused lecture. This is meant for discussion only. That is fine. Okay. So what I said is, let's say we want to map from Rn to Rm. Okay. So what we want is we want m vectors on whose span we can sort of uh, like represent these vectors. Okay. So let's say how we are going to find these VIs, I'm going to tell you. But let's say we are able to find m vectors, let's say v1, v2, vm. We were able to find out. Okay. Then how do you obtain? Let's say you have a data point x1, x2, x3, xn. You have this data point in n dimension, Rn. You're looking for a data point in Rm. And you have find these m directions which are useful to you. Okay. So how do you convert from this to Rm? That you can obtain. Let's call this point as, let's say, P. Okay. So that you can obtain by taking P transpose V1. So this is a vector that I'm creating. Second entry is P transpose V2, so on till P transpose Vm. So these are just vectors, so these would be single entries, and this vector hence would be a Rm vector, right? Yeah, definitely M is less than N. We want to do dimensionality reduction, right? Whoever asked this question, if I miss that thing, that is definitely less than N. Okay. So this is how we can obtain a transformed vector after we have found V1, V2, Vm. Okay. So the main task over here is to find how do we find V1, V2, Vm. Okay. Before going there, one more motivation. I will be very loosely speaking over here, but let's say you have a two-dimensional data. So I said that PCA will try to find a vector that should preserve some information. So what kind of information PCA sort of focuses on? Okay. So if you have variance in the data, okay, so if you have data that are spread far away, let's say you can see that in this direction data is spread a bit, right? This point is here, this point is here. Compared to if you look in this direction, the data points are much closer to each other. This is here, this is here, this is here. But if you look in this direction, black line, the data is much spread. Okay. So PCA looks for a direction in which data is most sort of spread. Okay. So it tries to maximize that variance. Okay. That if you will look at the proof that is discussed in the lecture, that would be clear, like how it does. So if you will do a PCA, you will get a line something like this. So it would ask you to project on a line something like this. This might not be very accurate. It can be something like this also, but yeah, something like this only. It will ask you to project on this line. Okay. Okay. Now I'll straight away go to how you find V1, V2, Vm for principal components. Okay. So this V1, V2, Vm that I mentioned above, those are called principal components in case of principal component analysis. Okay. In LDA, it won't be called principal component, but in PCA, these are called principal components. Okay. And these are eigenvector corresponding to largest eigenvalues of covariance matrix. So if you have a data set, you will find its covariance matrix, and then you will pick eigenvectors corresponding to largest eigenvalues. Okay. Now, if you see carefully, your matrix is of form C transpose C. Okay. So if you have a matrix of form A transpose A, you know that it's symmetric. It will have real eigenvalues, and more than real eigenvalues, it will always have positive eigenvalues. Right. So you need not worry about the sign of eigenvalues over here. You will have some largest eigenvalues. You pick the eigenvectors corresponding to those eigenvalues, and those eigenvalues will be your those eigenvectors will be your V2, V1, Vn. Okay. I think in this notation again I have missed the notation. I will correct it. So if your x is your data points, this would be V1 transpose x, V2 transpose x, and so on Vm transpose x. And this is how you obtain your lower dimensional vector. Okay. One very small comment that I want to make. So I mentioned that when you have features mean equal to 0, then you can find the covariance matrix by doing 1 upon n minus 1 C transpose C. Okay. Even when you don't have your features to be 0, what you can do is you can find the mean and subtract the mean from column. Okay, then the new matrix that you will obtain, that will have mean 0 for that particular column. And this is a very common practice in machine learning. If you have data points, you take the mean of the feature and you subtract the mean out from that feature. We also sometimes normalize the feature so that some features don't dominate too much. Okay. So it's a very common practice that you subtract the mean from your data column and also divide it by the standard deviation. Okay, this is a common practice. So if you do something like that, you are not doing something bad. Okay. Okay. I think this is the question, but we should have had a question on PCA. Okay, yeah, we have a question later on. Okay. Okay, so whoever asked like how would we calculate those matrix multiplication, those kind of things, I think in exams these kind of questions would be more dominant. But again, this is my opinion. I think that will again depend on the professor. Okay, so the question is, if the direction of principal components are these, so these are your vectors v1 and v2 that we talked in our notion. Okay, and you want to reduce this data point 1, 2, 3, what will this map to? This is the question that is asking. Okay, so we just discussed that if you want to find the lower dimensional representation of this data point, okay, this would be p1 transpose x if this is my x, and p2 transpose x. So this can be given by 1 by root 2 plus 0 minus 3 by root 2, that is minus 2 by root 2. Okay, and the second quantity is 0 minus 2 by root 2 plus 3 by root 2 is 1 by root 2. So this is just minus root 2 and 1 by root 2. This is the data in lower dimension. Okay, I hope this was clear. Okay, we will have a full example on PCA. Okay, we will try to reduce it onto one dimension. Because I'm hand solving it, I have picked up easier questions you can do. Okay, so there is one more important thing. I think this is related to what we did in last class also. So now, because you are picking up eigenvectors corresponding to the k first eigenvalues, okay, so I should stick to one notation. So if you are converting your data from Rn to Rm, right? Now, so what you are doing is you are sticking to eigenvectors only corresponding to the k largest eigenvalues. Then the amount of information that you were able to preserve, that is given by sum of eigenvalues up to m divided by total number of eigenvalues multiplied by 100 would give you it in percentage form. If you don't multiply it by 100, you will get a fraction out. Okay. Okay. So this should be clear. Okay. Now this is the C that is given to us. We have two features. Let's call them x and y for simplicity. This is 2, 1, 3, 5. For some of you who have done some machine learning course, this y is not the label. This is a feature only right now. Okay, right now we have not come across any label of those kind of things. We are just dealing. So generally people write x comma y, where x is your feature and y is your label. Right now this complete thing is only x. We have not come to y. This is also a part of feature only. Okay. 4, 3, 5, 6, 6, 7, 7, 8. Okay. Now you can clearly see that its mean is not 0. We don't have any negative entry, so there is no hope that the mean would be 0. So there are 1, 2, 3, 4, 5, 6 points. And the mean you can calculate 14 to 27 by 6. Mean over here is 27 by 6. So why not? So I think my complete screen is visible to you guys. Can you see this MATLAB screen? Can some of you please confirm whether you are able to see this MATLAB screen?
Yes,
Yes,
yes.
sir. Yes.
So let's try to write this data point there. So I'll clear all this thing. So my C is given as 2135. This is 2135. Right. Then it is 4, 3 and 5, 6. 4, 3, 5, 6.
4, 3, 5, 6, 7, 8. 6, 7, 7, 8.
Okay, 6, 7 and 7, 8. Okay. Okay, so I said I'm doing it by hand, but I didn't want to calculate the mean too. So mean, it gives me the mean of every column. So this is 4.5, 27 by 6 is definitely 4.5, 4.5, and this is 5, right? So we want to obtain a matrix, let's call it C modified, okay, where we want to subtract every entry of first column by 4.5 and every entry of second column by 5. So first entry would become minus 2.5. This would become minus 4. Similarly, this would become minus 1.5 and this would become 0. So we can do it over here also. So what we want to do is we want to do C minus mean of C, right? So this is what we have obtained. So let's name it also. Let's call it C modified, right? So we have obtained our C modified. And this is same as we would have obtained over here also. I have done nothing, I have just subtracted the mean. Okay. Now because my mean is 0, what I can do is I have to obtain the covariance matrix in order to do PCA, right? I have to do find covariance matrix. What is covariance matrix? This is 1 upon n
C
minus 1.
trans 1 by n minus 1, C transpose C.
Now this C is C modified, right? This is C modified transpose C modified, right? Let's see what we obtain for this C modified. So what I'm doing is C modified transpose. This dash means transpose, and this is C modified, right? And this is what we obtain. Okay. So n I think was 6, 1, 2, 3, 4, 5, 6. So we divided by 5, right? So this is 17.5, 22, 22, 34. Right? So let's call this covariance. COV we can call, or COVM. COVM, let's call it. I'm saving it so that we can use it later also. Okay, and I divide it by 5. Right, so I obtain 3.5. After dividing it, I obtain 3.5.
Sir, is the answer obtained
Is the
is
answer
correct? It must right. Yeah, sir. Correct. Correct. Sorry. Correct, sir.
6 point? Because I'm not doing by hand, I can trust the software. I can. That's why I'm not doing by hand. I might make a lot of mistakes. Right. Okay. So this is the covariance matrix that we obtain. Okay. Now in order to find our V1 and V2, now we want to reduce it only to one dimension, right? So we are just looking for V1. We can ignore V2. We want to find the eigenvector corresponding to largest eigenvalue, right, of this matrix, this covariance matrix. Okay. So let's try to find out eigenvector of this eigenvalue. Let's first try to find out. Okay. So eigenvalue is 0.4508 and 9.8492. I'm sure you won't get calculation like this in exam where you have to find this decimal kind of eigenvalues. That I'm pretty sure. Okay. Okay. So these are the eigenvalues. Now which one of them is bigger? Definitely the second one is bigger. So my V would be eigenvector corresponding to this. Right. So MATLAB also has that option available for us. We can look at the eigenvectors too. So for the second one, the eigenvector is, your V is 0.5696 and 0.8219. Okay. Now this is the V that we obtained. Okay. Now for any arbitrary point, let's say we began with data set having point 2, 1. We wanted to convert it to a one-dimensional vector. So now 2, 1 would be mapped to 0.5696 into 2 plus 0.8219. This would be its one-dimensional representation. And similarly, you can obtain for others also. Okay. So if you had 3-dimensional to 2-dimensional, you would had V1 and V2. Then similar to the previous example, you would have done V1 transpose X and V2 transpose X to obtain a 2-dimensional. Okay. Even though I have not covered the derivation of this PCA, I hope at least this is clear. How do we calculate like how do we reduce and how do we calculate the PCA if you are given with some arbitrary data matrix? Is there any doubt in whatever calculation we did, any step that is not clear?
Last step, can you say, after that eigenvector, uh, we found the eigenvector now.
Okay, after we have eigenvector, that is not clear, right?
Yes,
Okay,
after that.
okay. Once you have the eigenvector, okay. So what does this eigenvector will give you? This is the direction in which you want to project your points. Okay. So how will we project our point is, let's say you have a data point X. This can be projected in this point by taking X dot V1. So this is what we have done. So our X was 2, 1, right? So what we did was we projected it using a dot product. So 2 multiplied by the first element plus 1 multiplied by the second element. And whatever value we will obtain would be the one-dimensional representation of this point. Okay. I hope this much is clear. Is this clear? Then I'll say one more line to complete this sum. I think Vishnu was there who asked.
Yes, yes, I understood.
Okay, now
Now I understood.
now what I said later on was, this was example where we had to convert R2 to R1, right? So we had only one dot product. Okay. Now let's say you had an example where you had to convert R3 to R2. Similarly, you can extend this to Rn to Rm. So if you have R3 to R2, then you will have two vectors. You will pick two top eigenvectors, right? So now you have two vectors. Now you want to convert to R2. So your first entry will be V1 transpose X, that is V1 dot product with X. And the second entry will be V2 dot product with X. This is how you will obtain a two-dimensional vector. I hope now it's clear. Okay.
Yes,
Okay. So yeah, I think we can take a break for 2-3 minutes, and then we'll start this linear discriminant analysis. This would be not. It
Sir,
won't take.
what,
Yeah.
sir, we can take a break, but
You can ask me.
before going to LDA, I want to calculate the percentage of the projection and the
Okay.
PCA.
Percentage of information
After
preserved.
the break, after the break, yes.
Okay. So it's 7:15. We can meet at 7:18. Okay.
Yeah,
And
sure.
then
Thank
then
you, sir.
then we will try to solve for this particular example only. What is the amount of information?
Yeah, sir. Thank you.
Okay. I hope I'm audible again. So there are a couple of questions in chat. I'll try to see if I can answer them. So somebody has asked, sir, what is the relation between SVD and PCA? SVD means single, SVD is single decomposition. So I think it was covered in the lecture, but I'll briefly tell you what it is. So if you have this matrix C, which is your data matrix, and you find SVD of this particular matrix, okay, then columns of your B are in fact your principal components. Okay. So this V1, V2, V3 that we talked about are indeed the columns of your B matrix that you will obtain by taking singular value decomposition of C. Okay. So that I think is evident how it is that what you do is you find eigenvectors of matrix C transpose C, right? This is your covariance matrix by some scaling factor, obviously, but this is the matrix that you do. And when you do SVD, your V matrix columns are corresponding to eigenvectors of C transpose C, right? So they both are same thing. So your columns of V are nothing but your principal components. This is what the relation is. Then somebody says, can PCA be applied to dependent variable to create an index? Ravanan, I'm not very sure what do you mean by dependent variables to create an index. Okay, dependent variables is okay, but what do we mean by creating an index? If you can uh, say something more about it, I will probably try to answer it. Like, what do we mean by creating an index? Okay, now before going for the break, somebody asks how can we find this amount of information preserved? So I'm not a very organized writer, so I will try to use this space to answer the question. Okay, so as mentioned in the formula, the amount of information is given by, so over here in this example, we had two eigenvalues, right? And we used one of them. So what you will do is you will write all the values that you have used divided by the sum of all eigenvalues. Okay. Into 100. So this is sort of a measure that you will obtain. So this is the amount of information that you are preserving when you are going from 2 dimension to 1 dimension. This is the formula that you are going to use. So if you had used more principal components, so you would have written on top sum of all those eigenvalues, and in the denominator you would have all other. Okay, one of the aim of it is to avoid multicollinearity. Okay, so can it be used for dependent variables where there is no issue of? I think like if you have dependent variables, they are correlated, right? If I'm not wrong. So having dependent variables means that they are correlated, and those are the situations where you're going to reduce it to lower dimension. So you should like these methods are meant for these kind of data only, where you have your features are dependent. Okay, so this dependence word in machine learning comes in both the directions. So what I'm getting out of your question is that you want to ask, what you want to ask is, let's say my feature F1 and F2 are dependent. So if my features are independent, then your correlation that you get or the covariance that you get, that would always be 0. Okay, then there is no point in doing all this. This would be useful only when there is some dependence between your features. Okay, Now the second form of dependence comes through when your data points are dependent on each other. There I don't know what to comment, but if you meant that your features are dependent, then you should use it, right? Okay. Okay, so I'll try to motivate linear discriminant analysis. Okay, so I didn't explicitly derive, but what I mentioned was the direction of your PCA that you will obtain will try to preserve maximum variance. Okay, so let's say you have this data set, okay, and somebody asks you define a rule so that you are able to separate these two classes. Okay, let's say I have a random point here, and somebody asks you to which class does this point belong. Then you will in a go say that it is a blue point, right? So your mind can do it, but if you want to explicitly make a rule, maybe you can draw a line here and you say anything on the left of this is red, anything on right of this is blue. Okay, so this kind of data sets are called linearly separable data set. Okay, so what we mean by linearly separable data set is, so if you have a two, I'll just first define for two-dimensional data. So if you have a two-dimensional data and both the classes can be separated by a line. So if you draw a line on one side of that line, only one of the classes lie, then that kind of data is known as linearly separable data. Okay, so if you want to generalize this in higher dimension, so if you have a data in Rn, it is called linearly separable if there exists n minus one dimensional hyperplane. Hyperplane, I'm not sure if you have hyperplane heard this word. So in one dimension you call it a line, in two dimensions you call it a plane. In higher dimension, something generalized version of this is known as hyperplane. Okay, so it's called linearly separable if there exists a n minus one dimensional hyperplane which separates your classes. Okay, which separates your two classes. Right. So I'll okay. So let's get back. Let's look back at this picture. So what I said is your PCA would give you a line something like this. Red, we have red points. Let's use green. Okay. Now, if you project your points onto this, you will get this red point, this red point, this red point, this red point, and this red point only. And you will have blue. I'm not drawing squares, I'm just drawing this only. You have this square, this is your, this is your. Okay. Now your data set earlier was linearly separable. You were able to separate it easily. But now if you look, when you have projected it onto this line, your data set is no more linearly separable. Right? So this is not a good thing, right? Earlier you had linear separability. Now you have lost upon it. And linear separability is a very, very good I can give you an intuition. So if you have a linear separable data, some of you who have done deep learning, you can learn to separate them just using a single perceptron. Okay, so you can simplify your model a lot. Okay, for someone who has done machine learning, your linear regression is sufficient to obtain very good results. Okay, so losing on upon this property is not something that we want. Okay, to avoid this, we propose something known as linear discriminant analysis, or LDA. Its goal is that if your data is linearly separable, okay, then it will try to keep it linearly separable only. Okay, and then find the such directions for it. Okay, so the concept is similar to your PCA. Here also you will find vectors v1, v2, vm, and then you will transform. Definitely, yeah, both these techniques are used to reduce dimensionality. It will so when you map your points to a line, then also you have reduced your dimensionality, right, from 2 to 1. That was the main aim of projecting onto a line. Okay, so when I'm saying that we project, that means we want to reduce the dimensionality. Okay, so if you have v1, v2, vm, okay, then again you will obtain in the same way v1 transpose x, v2 transpose x, and so on. Now the way we find the v is different over here. Okay, so I'll define these things. First we are doing okay, I'll define this thing. This whatever I have written over here, this is only when you are going from R2 to R1. Okay, I'll tell you what we have when you go from Rn to Rn, but after solving this example, let's first solve for R2 to R1. Okay, so let me define terms that are present over here in this formulation. Okay, this is I'll tell you why I have written this. I have later on written it. Okay, so let's say you have a data set like this, right? Okay, let's now we are talking about linear separability. So we have labels also now. Okay, let's say this is feature 1, feature 2, and we have some associated label also. Let's say this was 2, 1, and the label was 1. This is 1, 2, label was 1. 3, 3, label was 0, and 1, 4, label was let's say 0. Okay. Or let's call label as 1 and 2 because you won't get confusing notation otherwise. Okay. Now what we will do is, our first step is to separate data of both the classes. Okay, this is our first thing that we are going to do. Whenever you are asked to solve a question, you will create 2 different divisions. First one containing your class 1 label, second one containing your class 2 label. So you will create a C1 that would have only now 2, 1, 1, because this is the label. So 1 you can ignore because you know that this is corresponding to my class 1, right? Then you will have 1, 2. And similarly, you will have a C2, which is 3, 3, and 1, 4. Okay. Remember, you have feature F1, F2 here also. You have feature F1, F2 here also. Okay. Now we define something as mu1. Mu1 is the mean of your C1. So the part where you have the stored your first class. Okay. So you take the mean. So this is 3, divided by 2 is 1.5. Okay, and again 1.5. So your mu1 now is the vector of size which is given by the number of features that you have. Okay, similarly mu2 is 2 and 3.5. Okay, so if you look at this formula, we had this mu1 and mu2 over here, and we have defined what are mu1 and mu2 are. Okay, so if you had the data, you first wrote them separately in classes, right? And then you found out the individual means. Okay, this is how you write mu1 and mu2. Okay, then you have something as SW inverse. Okay, which is sum of two matrices, which is S1 and S2. So this SW is sum of these two matrices, not the inverse sum. So this SW is S1 plus S2. You will find out this matrix and then take its inverse and then multiply it with this. Okay. So which is given by summation of xi minus mu I, xi minus mu I transpose. Okay. And you will have this only belonging to class 1. Okay, so this xi will belong only to C1, and here your xi will belong only to C2. Okay, so what you do is you subtract individual means from it, you multiply it with its transpose, and then you take the sum. Okay, now just a small thing, this xi is a vector, mu I is a vector, so the output that you will get is a vector, and its transpose is of this form. So the output that you will get is a matrix. So you are summing up many matrices over here. Okay. So this S1 that you will obtain is a matrix. Similarly, S2 that you will obtain is a matrix. Okay. And this is the formula for obtaining your B. Okay. So there is a lot of calculation involved over here, and there is an easier way to do this. I'll tell you what that way is. Okay. So let's look at this term. So this is nothing but summation I belonging to, let's say, C1. This is what we had. Xi minus mu1, xi minus mu1 transpose. Right. Now again, like we have this data set, what we can do is we can make their means 0. Okay, same trick we can use. So if we make this mu1 and mu2, yeah, to be 0. Let's try to work out this without making it 0. Let's see if we are able to achieve something. Okay, let's see if we are able to do something. Okay, so this is xi minus mu1. So this is sum of all these matrices, right? So its first entry, if you look at the first entry, this would be x1 minus mu1, right? We are talking right now in terms of two dimension. So this x, this would be something like this. Right? And then it's transpose, right? Mu f2, right? And then you are summing it over all the, you can add I over here, and you are summing it over I, right? So if you look at this matrix, the first one is x1 minus mu f1 square. Second entry is x1 minus mu f1, x2 minus mu f2, right? This is x2 minus mu f2 multiplied by x1 minus mu f1. This is just matrix multiplication that I'm doing, right? x2 minus mu f2, right? Do you recall this matrix? We have seen this matrix somewhere today. This is sum. Sum
X
can
to
go inside.
square, right? X2 minus mu x to square, right?
This would be square, right? Right. So have we seen something like this where you can see that this sum can go inside, right? Because you're summing all these matrices. So let me push this inside. So this sum can go inside, right? Have you seen this matrix somewhere? If you compare this with correlation, so this is nothing. This looks something like variance, right? But we don't have n minus 1 term over here. Okay. So this is nothing but this is n minus 1 times, because we had a missing n minus 1 of covariance matrix of C1. So this term over here, this S1, is nothing but n minus 1 times the covariance matrix of C1. Okay. And again, how do you calculate the covariance matrix? You take 1 upon n minus 1 C1 transpose C1, given the condition that your mu1 is mu of f1 and mu of f2 is 0, right? You can make that happen by subtracting by appropriate mean. So what you can do is, so this is the covariance matrix and this is it. So this S1 is nothing but C1 transpose C1 if you subtract your mean first, right? And similarly, you can obtain the second term S2 also. Okay. So now if you just rewrite this, if you break this thing, then your calculations become pretty easy, right? So what you have to do is you have to first, whatever data set that you have to write it in C1 and C2. Then you will calculate U1 and U2. You will subtract this mean to obtain something known as, let's say, C1 modified or C2 modified. From here, you can easily obtain this S1 and S2, and you can put it in this formula to obtain your V vector. Okay, at least when you're going from 2 dimension to 1 dimension. Okay, for example, here they have explicitly, this is a question where you have two classes, and these are the data points that is given to you. They have explicitly mentioned elements of both the classes. Okay, and then they have asked you to find the linear discriminant analysis, this D vector. Okay, so we can do this thing easily, right? So let's try doing this at least for this example. So we have this C1 as 422423. This is 422423 3644. Right. This is the C1. And then C2 you have 9, 10, 6, 8, 9, 5. 6, 8. 8, 7, 10, 8. Right. These are the matrices that we have. Okay. So first of all, let's try to find out mu1. Mu1 is mean of C1, which is 3. So we have now mu1, which is given by 3 and 3.8. Right. Similarly, if we look at mu2 is mean of C2. This is 8.4 and 7.6. Okay. Now we have to find S1 matrix. So what I will do is I'll subtract mu1 from C1, take its transpose and multiply it with, I hope this is clear, right? So S1 will obtain to be this 4 minus 1 minus 1 8.8. And similarly, you can obtain your S2 by just replacing this 1 by 2 everywhere, and this is 9.2 minus 0.2 minus 0.2 and 13.2, right? And you can now
You,
obtain your,
can,
yeah.
can you hold the screen for a while? I am taking notes, please.
Which screen you want me to hold, the MATLAB one or
Yes,
this one?
this screen, sir. Yeah, presenting screen, not MATLAB. Wait a second, sir.
Okay, so I'll
You,
upload this. You can access it from there also, but yeah, I'll hold it right now.
sir, how did you calculated mu1? Is it corresponding to x1, right?
Only corresponding to x1. So this is 4 plus 2, 6 plus 2, 8, 11, 15, right?
15 by 5, right?
15 by 3.
Correct.
Okay, got it. That's how I've
Thank you, sir.
obtained it. Okay. So now SW, as I mentioned, is sum of these two, right? So this is this plus this, and you obtain something like 13.2. This is minus 1.2 minus 1.2 and 22, right? This is the SW that you have, and let's save this as SW only, SW, and I want to take SW inverse. This is how MATLAB gives you inverse. So SW inverse is 0.0761, 0.0042, right? So the V vector that you will obtain now is SW inverse mu1 minus mu2, right? So you have your mu1 and mu2. So I'll just straight away calculate this thing multiplied by, you had mu1. Now this MATLAB has given me mu1 as a row vector. That's why I'm taking its transpose. Otherwise, the formula is same what I have mentioned. So this is the vector that you obtain. This is minus 0.4629 and minus 0.1960. Okay. Now you can, so you have obtained your V, and you can now obtain the projections accordingly. So this is about going from R2 to R1 in LDA. Okay. Now you see whatever is mentioned over here, using this formula, you can only obtain one V. Okay. But if you want to go from, let's say, Rn to Rm, okay, you want more V's, right? You want V1, V2, Vm. Okay. So what are V1, V2, Vm in that case? I'll just mention it. The calculation over there is not that straightforward. SW, definitely you can obtain the way we obtained right now. There is one more term, right, which is called SB, which is given by this formula. Okay, you have calculated mu1, you have calculated mu2, you will calculate mu1 minus mu2. This would be a column vector. Then you will have mu1 minus mu2 transpose. This will be a row vector. you will obtain a matrix by multiplying both of these, right? This is SB. So this product that you get, you look for k largest eigenvector. By k largest eigenvector, I mean eigenvector corresponding to k largest eigenvalue, similar to what we did in PCA. So in PCA, we looked for this covariance matrix. That covariance matrix role over here is replaced by this SW inverse SB. SW we calculated S inverse, SW inverse. SB is given by this matrix. Okay. This is how you will obtain the V1, V2, Vk. Okay. Okay, so this is what I had sort of prepared for today. If you guys have any doubt, you can ask.
Sir, for LDA, we are having some set of sample points, right?
Right.
Whether it need to follow any kind of population, like whether it follows any discrete or continuous distribution. Is that any criteria for that, for doing LDA?
Okay, so there is, I think people assume that if it is Gaussian, then it works well, right? But people have tried it for other things also, because in machine learning generally you don't know what kind of distribution they follow, and people have used and they have got good results. But there is something where people say that it works well for Gaussian. So if there is some question related to that, you can take Gaussian over there. I hope you
Pardon, sir,
understood.
I didn't get you, sir.
So what I am saying is, there is some theory which says it works well when your data is sampled from Gaussian distribution, right? This is a known like theoretical result, but people have empirically. So in machine learning, there are two things: something that are theoretically proven, and something that is just works empirically. So when you have your data, some real world data, you don't know from what kind of distribution it has come from. If you know that, most of your problem is solved. Okay. So then people have tried using it on different kind of distributions also, and it has worked well. So theoretically, we know that it works well for Gaussian, but if you want to use it in practice, you can use with other distributions also.
Thank you, sir. Thank you. Why I am asking this means, if whether if it is follows standard normal distribution means automatically its mean will be zero, then we can easily convert the given data set into C transpose C. Like that is what I am asking.
That is not required. Like that is not necessary that it will follow standard normal. It followed Gaussian, or you what we call normal. But standard normal is not something that is guaranteed. I'll post these notes for sure.
Sir, two more thing I need to ask regarding the previous assignment. In the first question regarding eigenvalue decomposition, a question is asked, but